So today we have the pleasure to welcome Gareth from the University of Cambridge. And Gareth is going to talk about stability of the dust. So feel free to ask questions during the presentation, and you have the floor. Thanks a lot for being here.
Yeah, thanks a lot for inviting me. It's been really great so far meeting everyone. Yeah, so I'm Gareth. I'm going to be talking about mostly a paper that I wrote with the collaborators at East Island, Mara Stovieva, and my supervisor, Ulrich Sperhake. So the structure is sort of going to be in four parts, one of which is more work in progress, so I'll speak good at the end if I have time, basically. And basically, the paper I'm going to talk about into three parts. So first of all, the motivation, the background, what we're doing and why, and what sort of general lessons we think we may have learned about doing numerics for these objects along the way. And I'll talk very briefly about the perturbation theory, because that's sort of what we're going to be looking for departures from in this project. And we'll talk about the actual dynamical evaluations that are the meat and potatoes, if you like, of this work. So getting started, what is the motivation for what we're doing? Well, the motivation is that we believe that there, of course, are black holes out there in the universe, but the observational evidence that we have for them, things like the BLBI images and the fact that we have gravitational wave signals that we detect that are entirely consistent predictions for black hole binaries. Really, these often only direct to the existence of objects which have light rings. And not necessarily horizons. So this leaves out the possibility that there could be a population of ultra compact horizonless black hole mimickers out there that have light rings imitating black holes, cast shadows imitating black holes. Their light economic exponents could be the same in black holes. Sort of leading order ring down behavior to be the same as well. So what are we going to look at as candidate objects for this kind of object in this paper? We're going to look at boson stars. Now, I know there are a lot of people here who know very well what a boson star is, but for those who don't, they're essentially what you get classical level when you couple a complex scalar field minimally eclipsed to gravity. You then make harmonic condensates of the following sort, where the time dependence oscillate in time with some value of omega that you shoot for in the complex plane. And omega is going to be a different omega for every central amplitude that you feed in and solve for. And when you work out the possible models that you can have in this theory, you have a one parameter family of solutions. You also choose a potential. So the ones that we're going to be focusing on in this project, the simplest one is just the mini boson star potential, which is a massive Klein-Gordon potential. The one we're really going to be interested in is this solitonic boson star potential, where you have this additional degenerate vacuum state at a field amplitude sigma naught or square root of 2. And this degenerate vacuum is really what's going to allow us to construct very, very complex models, plotting the mass against radius. Boson stars don't have a hard surface, so we define the effective radius as that containing 99% the mass typically. We're plotting these against each other here for mini boson stars in a solitonic family for sigma naught by 2. As we'll see, this is actually not a super compact family of boson stars, but already we can see that the compactness that you can achieve with the solitonic family are significantly we can get just with mini boson stars. So why do we like boson stars in numerical relativity? Well, they're very, very easy objects to evolve. There's no fluid, you're just solving a nice thing Klein-Gordon system, so you don't have to worry about it like shock capturing, all the horrible complexity of neutron stars and so on. So they're really, in many ways, the simplest compact objects from black holes, I suppose, that you can evolve in numerical relativity. But can we construct ultra-compact objects with them? And the answer is yes, we can. And the way that we do that is essentially crank down this sigma naught parameter in the solitonic potential. We're still just considering spherically symmetric models here, but what I'm plotting here is the ADM mass against central amplitude for the two families, sigma naught 0.06 and 0.08, that we're going to be interested in looking at in depth in this project. And as you can see, you get very, very massive models that have log scale of the y-axis there. You get very, very massive models towards the peak there. And the yellow region is going to be the region where there are light rings, where you have ultra compact objects, where you have black hole mimics. And as you can see, so the classical stability theory, as I'll talk about in a bit, really predicts that everything from this minimum mass down here to the maximum mass up there is going to be perturbatively stable. So there's a relatively small range of the parameter space when you have two black hole emitters on the stable branch, but it is there. And so we can we can do things with these models without them at least immediately blowing up, which is good news. Now, you may ask, why do we call these thin shell models? And the answer to that is plotted here on the right. So I'm plotting the energy density essentially as well as the Kretschmann scalar in between the location of the light rings at our mid and our max there for one of these compact objects, the ring one, the ring box essentially that I plotted over there. And so you can see that the energy density profile is really essentially a shell of energy. There is some contribution in this feature, but it's entirely dominated by the gradient terms, where this is a scalar field profile now, and where it falls off very sharply. Because if you like, the intuition for this is that you pass the degenerate vacuum state with a bunch of matter over here near article 0, and you're transitioning to the vacuum state to value 0 at large R, and transition between these it's going to have a large sort of shell-like energy density distribution.
So, yeah.
Yes.
So the way these are stable, you need
Against radio perturbations. Yeah.
there's no data check.
No, indeed, yeah, only radio perturbation. Yeah. No, that's definitely true. Yeah, the mode analysis for boson stars in general hasn't been done to nearly the same extent as neutron stars, for example. So there's been also some work in the past in our group, not with ultra compact boson stars, but with fluffy to relatively compact boson stars, where essentially the question that you ask is, you have a boson star binary, you feed in the gravitational wave signal that you get out to your favorite gravitational wave data analysis pipeline. You ask it the question, what do you think the parameters for this black hole binary, even though it's not a black hole binary, are? And do the residuals or something else suggest that there are problems here, there's smoking gun effects that this can't be fully explained as a black hole binary? And the answer is that in many cases, no, there is a significant degeneracy. It'll happily misinfer the parameters, the mass ratio, everything else for your boson star binary, assuming that it's a black hole binary. There are sometimes smoking gun effects, but where you generally see those is where the boson stars are not very compact and where they don't leave a black hole remnant, but a boson star remnant, because the ring down is really different in those cases. And this is very much not going to be the case for our ultra compact models. They're obviously very, very compact, and if two of them can collide, they would certainly leave a black hole. It's certainly plausible that there would be an even greater degeneracy with gravitational wave signals from black holes with these kinds of objects. So again, pointing out the fact that a lot of the observations that we make don't necessarily exclusively point to black holes in the universe. Now, there's this argument, again, some people here will know very well, that there's a big problem with this hypothesis, which is that ultra compact objects may be generically unstable. There's some analytical work, some numerical work that's been done to argue this point. The reason for this essentially is that light rings for ultra compact objects come in pairs, one of which is sort of roughly the unstable light ring that you get also for a Schwarzschild black hole, but then there's one on the inside of that is a stable light ring, meaning that massless perturbations you expect to potentially be trapped there. And the gist of this idea essentially is that massless perturbations are trapped at the location of the stable light ring over time. They build up, back react, and destroy the ultra compact object, either collapsing into a black hole or migrating into some non-ultra compact configuration. So this is sort of what we set out to test in the case of our spherically symmetric models, just trying to answer the question, do we see any evidence whatsoever for departure when we evolve these models in full 3+1 in axis symmetry and spherical symmetry from the predictions of sort of the radial perturbation theory, which for spherical symmetric boson stars in general depicts captures their dynamical fate almost perfectly in other cases. So do we see departures in this case? And if so, at what level do they manifest? So the first step answering that is to actually ask the question, what is the perturbation theory for these models? What does it tell us about radial stability? The way that you answer that is to make essentially simultaneous perturbations to the metric and scalar field variables. You reduce the system that you get to a couple of PDEs. You then take a harmonic constants for these. So really, this is just a mode analysis of the spherical mode, and you're of course interested in this fundamental mode, K0 squared, because if that is negative, or we have an unstable mode, clearly we have a spherical perturbative instability. If it's positive, then the fact that we have a Stern-Liouville problem, and we have this ordering of modes means that the other ones will all be positive. So we at least at the linear level have radial stability. So what does this look like for boson stars? Well, yeah, as I was saying, we're interested in the points where K0 squared, the fundamental radial oscillation frequency, is equal to 0, because that's going to be where you have a potential transition from stable branch to an unstable branch, or as we'll see, vice versa. So what I'm plotting down here on the left first is the parameter space for boson stars. Now the plot's a little bit busy. You have some instability timescales too. But essentially the takeaway is that from 0 to the first extrema in the mass central amplitude curve, which is sometimes called the Kalp limit, you have that as a stable branch, and everything on the right, as you can see, the red dots have moved up, which means we have an instability timescale. So indeed, everything beyond that is the unstable branch. And at further extrema of the mass central amplitude curve, you see that your higher modes go unstable. There's no second stable branch for many boson stars. For solitonic models, the situation changes a little bit. So you once again, from 0 to your first extrema of mass, you have one stable branch, then you have an unstable branch from that maximum to your first minimum of the curve. But when you go then from that minimum to your next maximum, and you'll see this is where our really compact models live. In particular, when we make sigma naught sufficiently small, where ultra compact models that we'll be looking at live, and you have a second stable branch. And so, the first question is, okay, let's crank sigma naught down really small and repeat this, compute these radio frequencies. Not only because this is going to verify absolutely that yes, even for small signals, still have radio stability, but also because this is going to give us something to calibrate our numerical simulations against and say, okay, if the oscillations that we observe are at something different from this fundamental oscillation frequency, then that's evidence that some kind of non-spherical mode is becoming important as the evolution progresses. And if we do that, then we see the following. So what I've done here is in the inset, I've block plotted the first stable branch, mini boson stars and solitonic models with a range of sigma naught values. I've also done it on the second stable branch here. You'll see that the curve actually self-intersects. That's because one thing that I didn't emphasize earlier, but in the Finchau regime, the central amplitude no longer uniquely determines your boson star model. There are this region where you have 3 models of low, intermediate, and high masses, all corresponding to the same central amplitude, and with different frequencies as well, and so on. And so, of course, here, yeah, unsurprisingly, we verify that we have the linear radial stability that we expect. We thought this second stable branch would be. We also see that the oscillation frequencies get very, very large. Some regions, this small sigma values, which is also interesting maybe, but we're really going to be interested in the masses, the models near the critical point. The oscillation frequencies are going to get close to 0 anyways. So let's move on to talk about that then. The dynamic evolutions of these models is really what we're super interested in.
It's like, you plan to do, what you
I don't think, yeah, not imminently at least. I mean, my intuition would be that for this project, probably the non-radio, like I would expect that the light ring instability would enter non-reductively. Um, and so for this project and this kind of thing, I'm not sure how useful that would be. I don't think there's a huge literature for mode analysis of boson stars beyond the spherical mode. And it's already, I mean, you can see that if you write out the full PDEs, and you know, I was already for these models, just was the fundamental spherical mode, you're running into problems. The shooting method becomes numerically very difficult. Getting overtones is even harder. And it's already sort of a more complicated problem than if you just do the analogous thing for the TOV equations or something. So yeah, no, it would definitely be interesting. It's not necessarily on my agenda.
so you need small, related to license, so the beam from the start, it's you know, that even in the main branch, minus analysis, you be things, I mean, say, and not even still, it's inspections, but they are no state, yes, and it's nothing to, like things to know, it's just things for still.
Yeah.
So, I mean, it would be interesting, I would say. That maybe one will get surprised to see this small or the other one.
Yeah, no, that's really true. Yeah, interesting. Definitely. Anyways, the dynamical evolutions. So as I said, we run in spherical symmetry and axial symmetry, and in full 3+1. Some in octant symmetry where you only run 1/18 of the grid, just to save on computational resources, but also some in case that was some has a pricing instability, full grid with no symmetry assumption whatsoever. Spherical symmetry. I wrote this code that I call spherical BS evolver. And the idea here is essentially that you dimensionally reduce the DSSN and CCZ4 systems. My numerical relativity people will know what those are. They're essentially two of the standard numerical relativity evolution schemes, one of which is constraint damping and the other DSSN is not. And the idea here is that you make as fair a comparison that you can with the higher dimensional codes because you're doing everything essentially by the same method, just with this dimensional reduction. Yeah, so my code's on GitHub if anyone's interested, although it's still in a somewhat messy state. But for the higher dimensional modes, the runs, we run primarily using this code GR Trombo. We also use the lean, which is a supervisor Uli's code. But GR Trombo, the key feature of it is this adaptive match refinement. Now, obviously, when we just have one model sitting there, you don't super need the adaptive match refinement principle. But it is nice to know about because you know, it means that if you were to do in spirals of these or even head-on collisions, any kind of non-trivial evolution of these models, you're going to save a lot of computational resources. So what I'm plotting here is sort of the grid profile of one of our thin shell models. And you can see that it's really resolved around the shell. Then the middle is worked out. Yeah, okay, scalar field profile is more or less constant here. We don't really need the same level of resolution. Another sort of you know, happenstance nice feature of the AMR, if you look very carefully, you'll notice this actually isn't perfectly strictly symmetric, even though our model of course is. That's because the algorithm that it uses to refine the grid, it's called Berger-Risotto's algorithm. And essentially it's not independent of the order in which it goes plane by plane, and it's dependent of what you put as the first plane along which to refine. And so generally with spherically symmetric initial data, it will not give you a perfectly spherically symmetrical grid. This is kind of nice. Speaking, it means that we have some non-spherical perturbation even beyond the level of just the pure noise here. So you know, this is a kind of a happy accident for higher dimensional lines, I'd say. So what are the results? Well, I'm plotting here the essentially the instability timescales for runs on the second stable branch, as well as the two unstable branches, it's left and right. There's a bit of overlap where you can really see it in the sigma naught 006 case, whereas the loss of HTML won't look like for the unstable branch. But again, this is just because there's a non-unique specification of the model with the central amplitude. And the takeaway here is that irrespective of the code that we use, the number of dimensions we reduce to, if any, we basically have perfect agreement with the perturbative results. So wherever we predict perturbative stability, we see that at least on a decent enough time scale, we see that. Wherever we expect instability, we see that as well. I should have mentioned, sorry, by the way, but black is 1D code, orange is the 3D code, and blue is the 2D code. So of course, we've not covered the parameter space entire dimensional codes nearly as well as with black, but wherever we have, we basically see agreement between the two. So of course, this by itself isn't just the best evidence that we have as for these lightning models in particular. So we took a really close look at these two models in the lightning regime for sigma naught 0.06 and 0.08 that we're talking about. So the important distinction between the qualitatively, so the sigma naught 0.06 model, this is essentially the difference in central amplitude from the initial value over time. You'll see we have very large perturbations, these relative to the drift that's due to numerical error. For the more extreme model, if you like, that's because we use the shooting code and in order to construct these models. And in order to construct them at all, you have to have quadruple precision. So we wrote it in Fortran. And even with quadruple precision, you're sort of getting with this model right to the very limit of what you can construct. And so there's this initial perturbation that doesn't damp away. But this is actually kind of nice because it gives us a very clean Fourier signal that we can compare to our computed radial perturbation frequency. And for the less extreme model, we're still in the lightning regime, but it's much less intense, as we'll see. This potential that determines the location of the light rings is much shallower in this case. And you still have some oscillations stemming from your initial numerical error in your initial data. But now you can really do a very clean convergence test and say, okay, is this drift consistent with being purely due to numerical error? And what we find is that yes, it is. If we do a Richardson extrapolation, which we're doing here, then you see that as you increase the resolution, you're limiting essentially zero drift at the order of convergence that we observe, which we'll talk about a little bit later. But it's basically in general between fourth and fifth order for these models.
Question.
Yes.
So do you been trying to put by hand some non-spherical perturbation as well, or is always numerical noise?
That's follow-up work. Yeah, so that's something I'll talk about at the end. So what we're doing now actually is hitting with the Tucholsky wave, because I think this will be one of the important things to resolve once and for all. What's happening here is an explicit non-spherical perturbation. But for this work, yeah, there's numerical noise. And see what happens with that, essentially. Yeah, so as I was saying earlier, we wanted to test these radio frequencies against the oscillations that we observe. So just a reminder, you get this very clean Fourier signal out in general. And so for our two ultra-compact models that we looked at closely here, you'll see that irrespective, stables are just different codes, the spherical code, the axisymmetric code, and one or both of the 3D codes that we use. But in both cases, we see very, very good agreement with the computed radio frequency. And so we can sort of suggesting that once again, for these models, even after fairly many times, it's still just this fundamental spherical radio mode that's driving the dynamics. We don't see other mode become important, nor do we see sort of any evidence at late times of anything else happening yet. Of course, you can always make the objection that, we need to run for longer and then use the evidence of, a numerical thing. This is a limitation of numerical work. So we're not saying, by any means that, these are definitively stable. We're just saying we run on these timescales, which are, over 1,000 late processing times, I think up to 2,000 now, because we've been running for a while since we submitted the paper as well. And we don't see any departure from the linear and the predictions of the linear theory, essentially. So, okay, that's all well and good, but that was all just sort of looking at the central amplitude. This doesn't preclude the possibility that our lightning structure has been destroyed. In other words, it doesn't answer the question, does the boson star remain ultra-compact? Maybe there's some dynamics happening at the light location. So to look at that, in a stationary strictly symmetric potential, your lightnings occur at the extreme of this potential H. You can see here again, I sort of verbally indicated this, but this is what it looks like for one of our boson stars versus versus a Schwarzschild black hole, just schematically. So light rings are going to occur at the extrema of this curve, and stability, as sort of in your classical particle and potential problem, is going to be determined by the sign of the second derivative at one of these points. So at the maximum here, you're going to have an unstable light ring. Of course, that's what you have in Schwarzschild, just the unstable light ring. And for our boson star, you're going to have this additional light ring that is stable inside of the unstable light ring on the outside. Now, of course, we're doing a full unconstrained 3+1 evolution, so our grid is not, our data is not going to remain perfectly spherically symmetric. So how do we account for that? And that's what we use is this adiabatic effective potential approach, which again is sort of adapted from something that's been done here. Where you define something that for a spherically symmetric spacetime reduces perfectly to this potential. And you check how the extrema of this function evolve over time. You're averaging the opposite shift of the sphere. So I'll build this up over time. So notice that, so I'm plotting here the value of this effective potential at time 0 and also at some time well into the future. And you can see that it looks like, this thing hasn't changed very much, but that's because I've cleverly started at the beginning of an oscillation. So if I run a little bit more into the future, then you'll see this thing is starting to shift. It still has extrema, plotting with the gray lines there. But there are some dynamics clearly. We went a little longer to was 870, and it's evolved a little bit more.
Sorry,
It's
question here. So if you account here for the change of last single,
yeah, it's just due to the numerical error, and it's very, very small. So you can do the way to account for it, I guess, in some sense, is to do a convergence test, because in the limit of resolution going to infinity, we find that our mass and nuclear charge are conserved. So for something like this, you don't really need explicitly to.
Because the daily effect after the unstable light ring, the location, the shape, or all depends essentially on the mass space. And so any changes should happen only after unstable light. So the fact that we have that behavior essentially is still I think it probably be accountable for the change in plan.
Yeah, we can do, we'll do, when we take, we plot the light limit speed, the decay of the light ring locations that's apparent is just due to the loss of scalar matter. Then when we do a convergence test, we see again that it's consistent with them not changing at all. So yeah, in that sense, we sort of account for it by convergence testing, if you like. Yeah, and you probably could, you're right, absolutely. The unstable light ring is just going to be determined basically by the total mass. So you could, in principle, work out where that's supposed to be just from the mass, but we don't really see we don't explicitly do that. But yeah, that would also be something we could do. But anyways, the idea here, so again, this thing is evolving, but over one oscillation period, you see now it's coming back down. And now what I'm going to do is flip this thing onto its side and sort of reveal what I've been doing all along, which is just looking at, these are our light ring locations, the unstable light ring at the top there, and the stable light ring at the bottom. And you can see that these oscillate quite significantly, even due to this relatively small initial perturbation. But the positions at which I've extracted the AAP are shown with the different shapes here, and you can see that the AAP evolves over time. It just has this periodic profile that always returns indeed. When you convergence test, you see that everything's consistent with the location of the light rings just oscillating with this profile forever. I've also plotted the potential difference between the two light rings in the inset there. This is again, you do the same thing. You see that this is entirely consistent with no change aside from this one oscillation at the fundamental radio frequency over time, and there's no evidence we can find of departures from this behavior. So now, of course, you can also ask questions about the robots. So what we're doing, and so in order to do that, we compute these relative variances over the sphere at late times. We take the standard deviation and divide it by the mean value over the square. So essentially, this is small. This is saying that yeah, you're roughly still spherically symmetric, and if it's large, then you may have reason to be concerned because you're getting away from the domain in which the AAP approximation can really expect to be valid. So starting just with the value of the lapse, yeah, that's pretty small. That's all good. When we add in the shifts and the value, this determines of a induced metric, which is really essentially used to convert to the aerial radius. So these are all the ingredients in our AEP essentially. You may be worried about the shift because that is not evidently small. But when you compare its relative magnitude to the lapse, you see, okay, it's just essentially it's only departing from zero at around double precision anyways. So we're just dividing a small thing by another small thing and getting something order one. That's not anything to be too worried about. So if I add everything else in here that we look at the paper now, so our lapse, our shift, our aerial radius essentially, the fact that these are all have very small variance over the sphere, and not variance that changes very much. If you look, we do it in the paper, you include the ranges through which these oscillate over time, and they change periodically again, just sort of like everything else in our evolution. So those three quantities tell us that our spherical symmetry is essentially being respected. The fact that the potential drop is much larger than the variance of the effective potential of the sphere tells us that light in extraction isn't getting significantly polluted, not more than sort of order 1% at least by non-sphericity in the profile. And yeah, the relatively small like the shifts verifies that we have stationarity relatively. So again, verifying the assumptions of the AAP hold true. And so what about our constraints? Because in numerical relativity, you always wants to make sure that your constraints are under control, so you can check that your evolution is reducing to the expected limit as your resolution increases. So what we see is constraint norms get to about fourth to fifth order at early times, or not late times, excuse me, at very early times, because we have sort of this large non-convergent error from our initial data, or maybe worse, to second order. But still, this isn't terrible by our standards. This is pretty common to have one behavior in one regime of evolution and another somewhere else. And you'll see here that what's happening is the constraints start off, sort of peaking and then level off over time. this is because we're using CCZ4, which I mentioned is the constraint damping formalism. If we use BSSN, which is a very similar formalism, but which doesn't have this constraint damping property, we see long-lasting linear growth, and this is actually something that people have seen in the past, right sort of the beginning of the CCZ4 formalism was looked at. So this is taken from one of the original papers, sort of comparing fluid stars, the Z4 to just their standard BSSN formalism. You see you have linear growth that goes on forever for BSSN, minus the log scale, of course. And for CCZ4, the two pairs are just with different boundary conditions, but either way, late times it levels off, it stops increasing. So linear growth, of course, the question to then ask, could linear growth be problematic? Is this sort of a numerical lesson that BSSN may not be the best for determining the stability of these objects? And we don't know the answer definitively. The reason that we might be a little bit concerned about it is that if you look at where the constraints are piling up for thin shell models, it's where you have the steep gradients right at the location of this thin shell itself, and that's right where your light rings are. So there's a potential risk that if you ran in BSSN long enough, and again, we haven't done this, but you could build up your constraint norms more and more there. And obviously, this is eventually going to lead to some kind of problem. We don't know what it would look like essentially. It would obviously be kind of a numerical issue, or if it would look conceivably like a black hole collapse or something else. But I think the takeaway message is that because you're going to have right where your dynamics are in general for these ultra compact objects, you're probably going to have steep gradients or some kind of numerical extremality, if you like, where your light rings are, and that's where your constraint violations are going to pile up from BSSN. So this could potentially be a problem. So we think that CCZ4 or another constraint observing scheme is possibly the way to go.
And about that, I mean, thinking in a different direction, do you think it is possible, really rule it out, that the constraint down CCZ will get rid of a time physically and physical growing mode? Because at the end of the day, you have a solution. You start with a solution in the base and strengths, but there might be a different solution in the 6.1 volt. And it's so good in constraint handling that actually you
Yeah.
if that's possible.
I definitely don't completely rule it out. This is why I think sort of the definitive test for these models is going to be adding explicit perturbations and something like this Tchaikovsky wave. Put this more at the end. But yeah, I think that's the only way to decouple completely. Because obviously when you only have numerical perturbations, the difficulty there is that you're going to have constraint growth at the same rate as you have physical perturbation growth. And so it could indeed be that CCZ4 somehow is killing off the modes that, lead to the buildup of perturbations at the light ring location, or it could be that these modes are just purely non-physical, not constraint violating, don't obey physics, are going to cause problems and non-physical behavior. We don't know right now. But yeah, I think explicit perturbations are the way to find out. Right, yeah, so I think you look pretty well, so I can talk a little bit about some early work involving information maybe. So this is brought us to the end essentially of this first paper that I just started talking about. Now we're going to talk about more about work in progress. So of course for astrophysical viability of anything, well, it better be stable on astrophysical timescales, but you'd also better have a formation mechanism. So we have one for solitonic thin shell boson stars, or are there bigger problems associated with forming them? Well, what do we know about formation of boson stars in general? We know from very early papers with mini boson stars that you can form these. So the canonical paper here is this Seidel and Suin, where they find that indeed, if you collapse a simple, massive, complex scalar field, you have some scalar radiation that is emitted at this gravitational cooling frequency, and you also Indeed, in the end, you form a boson star, a boson star. And not surprisingly, if you try this with a massless boson field, you get nothing big surprises. So the question, yeah, so as I was saying, the scalar radiation at this gravitational cooling frequency, but gravitational cooling is very, very slow. You can see these oscillations are very long-lived. And they have a total mass decay. You can see that already when they get to kind of this linear point, they may be somewhere to the regime where they had what we see, which is that numerical error starts to take over. It becomes a bit difficult to decouple what's actual physical radiation and what's just numerical loss of scalar matter. So what happens when we try this now for a solitonic potential? So here I just plotting a characteristic example for mini boson stars and a solitonic model with sigma naught 0.15. So this is well outside of the thin shell regime still. You're never going to form something ultra compact here, but it does sort of give us some intuition for where things might be going. And you can see information seems to be much more efficient. Your oscillations are settling down much more quickly relative to the mini boson star case. Again, if you think back to that plot I showed of the fundamental radial oscillation frequency, if you expect that this has something to do with the gravitational cooling frequency, then it's not surprising that these things settle down much more quickly. They oscillate at much higher frequencies. But what happens now when you go into the ultra compact regime? And that's that you see that these oscillations rapidly stop decaying. So initially you have, well, this is with sigma naught 0.06 now, so the most extreme solitonic boson star kind of looking at. You run for a while, you form something that looks like this, but it stops decaying any further. So what's going on here? To answer that question, it's useful to talk about what we haven't talked about yet, which is this notion of binding energy for a boson star. So of course, complex scalar field, you might have a conserved nodal current, nodal charge. The binding energy is essentially a measure of the energetic preference between all the scalar matter being dispersed to infinity and the boson star solution that you have. And we know that it's important because for unstable branch models in particular, determines their dynamical fate. So as you move along the any boson star curve down here, again, just mass against central amplitude. And so once again, your stable branch from 0 to this first extreme in the mass. So all these models are stable, but then on the unstable branch, your binding energy is still going to be negative, which corresponds to gravitationally bound state for a while. Models from here are going to be unstable either to collapse to black holes or migration back to the stable branch. But eventually your binding energy goes positive, and your models then start blowing out, dispersing to infinity, unstable diffusion, as some people sometimes say. So what happens when we look at this for our thin shell families? So this is again sigma naught 006. And there are two things that are interesting. So first of all, if you zoom in right on kind of the transition between the first unstable branch and the second stable branch, you'll see that there are actually some models where you have perturbative stability, but positive binding energy, as you expect in instability diffusion. So I sort of tentatively call this the unstable branch because you expect you can check this in my spherical code that if you just add some spherical perturbation, it will not generically destroy it. But you expect that if you add something sufficiently large, you'll be able to trigger fission and dispersal of boson star. And your ultra compact configurations then are very, very strongly bound, much more than you can get with the just mini boson stars up to 5 times the ADM mass down here. And so this means that perturbations are going to have a hard time escaping, essentially. And this is really, I think these two effects can kind of explain, or at least just hypothesis for what we were seeing before. The way that works is, well, first of all, I'll say a few words about these models that I call in what I call the metastable regime. You have potentially an instability fission, but derivative stability. I've added an explicit spherical perturbation, my spherical code, and run it. See that early on you have a lot of overtones, but at late times it's still not destroyed, and it just starts oscillating at this characteristic central. Yes.
So all these inputs are spherical symmetry.
Yeah, this is all. So far, this is all symmetry. Yeah. Yeah, indeed. So, yeah, and in general, in spherical symmetry, at least, it seems very more difficult than you would think, just by adding a perturbation to trigger this fission, essentially, that the sign of the binding energy would seem to predict. But anyways, if you look at the energy profile during one of these undamped oscillations that you see in formation, then what you see is actually that this is what happens when if you throw in a scalar cloud that has enough mass and nodal charge in principle to form one of these metastable branch models, but not enough to form a thin shell model, then what you'll actually see is you'll still have a thin shell-like structure emerge, but it'll oscillate. So this is kind of reminiscent of a real scalar oscillon. So for if you have a real scalar field, you can't have a boson star solution, something that's actually stationary. There's always going to be a long-lasting undamped oscillation to kind of source the kinetic energy that's necessary for something to for a stable model to exist. And it turns out that in this case, you see something a little bit like this, where this oscillation will just never decay. This is interesting because this tells us that this thin shell-like structure starts appearing way before we hit the light ring regime, and way before, if you just look at, sort of stationary Boson star solutions, you start seeing this convergence of the thin shell. And that's interesting, I think, because this means that, if you're trying to form this from collapse of a scalar cloud in general, it's not going to be the case that your thin shell structure just kind of pops out at the end, at the same point at which you see at which the late rings emerge. It's going to be really a gradual accretion of matter, but relatively speaking, the same kind of profile. This means that I think you can interpret this as being good for the prospect of being able to form this, because it means that you're not going to have a lot of very complicated dynamics right when this late ring regime pops to being, if you like, as you accrete scalar matter over time.
Chaos, but then if you do the degree to be more, you could just overshoot the maximum walls and collapse into a black hole.
Oh yeah, absolutely. Yeah, no, I mean, yeah, if you overshoot, yeah. So this is so I guess the perspective here, this particular class of models, we're definitely not saying, we expect to be out there in the universe, or even that it's, a terribly plausible candidate. But I think what's interesting as a more general principle is that, you start seeing something that has the same profile as any ultra-compact object early in the formation process. And it's not like the ultra-compact configuration, only enters very suddenly when you've already accreted a lot of matter, because this would cause more complicated dynamics and point up to us, maybe that would be where you're more likely to see instability where you're actually trying to form one. And so I think it's sort of suggesting the plausibility of forming one of these models by accretion of matter. Of course, we're not going to claim that this particular matter class is the correct one or anything like that. But yeah, this is straightforward. See too.
I'm gonna ask still another question, so because you have to observe things in branches, so the Amazonian and the Latvia. So what determines for an initial cloud if it will start in one or the other? Is it the mass, the cloud, or what the initial date?
The mass essentially. Essentially.
Right, but first in the Newtonian branch, mass the loss, it's the lower one in the yellow, right? So why do you think you choose to go into the relativistic rather than say forming a black hole that overshoot the mass or make the Newtonian branch? So very cool.
Yeah, so I think in general on the first branch, if you look go back to like the instability time scale, you generically we saw either migration back to the first stable branch or dispersion in the binding energy with those models. We didn't see black hole collapse there at all. Even when we started evolving unstable branch models. Now, of course, with other boson stars, it's known that like this can depend on the type of perturbation that you add and so on. So maybe that, if there's a risk to nearly causing a black hole collapse in general. But yeah, I mean, I think again, a lot more testing required here, and indeed, in particular, doing tests in the mass range of where you can form something on a Newtonian branch, as you say, that would be interesting to see if you still get this, or if then it's able to form something on a Newtonian branch. I think that would be very interesting. Or if this kind of oscillon-like structure that I see when you're forming something that would appear on what I call this metastable branch, which is really the start of the relativistic branch. Whether you still see that there essentially as well. Yeah, hopefully that answers your question.
Yeah, no, that's, I remember the paper, but paper by Sadler and Sven, actually, they start with more mass than the maximum mass, but it manages to shed away the excess mass, so that it falls out the mass state. But of course, in that case, there's one. So my question is, here, there's the probabilities to go to.
Yeah.
What Germany was one or the other.
Yeah, no, that's a very good question. I think it seems to prefer the relativistic branch is the short answer. But that may just be an artifact of the fact that I haven't, looked at the parameter space of initial clouds in sufficient depth yet. It's the short version of the answer, I think. So I was really just interested in, whether you can eventually form by gradual creation of scalar matter, the compact models. It seems like you can. So then going beyond spherical symmetry, I'll just mention quickly that we are planning to evolve non-spherical clouds using this CPDK formalism of initial data construction. So this is something that was developed fairly recently. If you know the CTT, the conformal trend or traceless formalism of initial data construction, numerical relativity. This is very similar. The idea is that instead of fixing your conformal factor, you solve the Hamiltonian constraint as an algebraic equation for K and follow the steps of the standard CTT method. From there, essentially, and this has been used successfully to construct initial data for things like spinning black holes with non-spherical symmetric, real scalar field clouds. We think it would also be good for formation runs outside of spherical symmetry. With complex scalar fields, seeing if the same kind of generic behavior happens when you drop the assumption of spherical symmetry, or if something else happens. I think we'll skip over this last thing, which is just that we're also going to use it for black hole boson star binaries, which is the other thing I'm working on right now. Write initial data for those to remove these kind of spurious oscillations that you generally get with binary initial data for boson stars otherwise. But yeah, I can answer questions about that if anyone's interested. But otherwise, it's the end. So what are we going to do in the future? So as I said, the biggest and most pressing thing I think is adding explicit non-spherical perturbations. I think this will, be our best chance at closing the book on whether we're really seeing stability of these models or whether there will be some instability that we just can't hit numerical perturbations on the timescales that we're running on right now. So, Tukowski wave adding small amount of explicit scalar matter accretion, a massive spectral field even would be a more extreme thing that you could do in principle, but would also, of course, if it's a light ring, you might as well add light. And of course, the extending the formation works, and you still have stability as you're forming these models in general. And then if you do find that these models are really stable, then of course that opens up a large number of interesting things that you can do with them, hadron collisions and spirals, repeating the gravitational wave analysis that's been done with less compact boson stars and seeing if there actually is, in this case, any chance of getting a smoking gun effect that could tell us, that thing that we think is a black hole binary out there in the universe maybe isn't. or if they're just totally degeneracy with black hole binaries, this is doomed, at least from the gravitational wave side, for an open problem. And then of course, looking at different compact models with our side of rotating models, Roca stars, frozen stars, and so on. Yeah, otherwise, thank you very much for having me, and I'll wrap up there.
Thanks a lot for your look and for keeping time. So we have more time for questions. Yeah.
This is,
Yeah. It's
so you made your point, just pointing that there will be, gravitational wave events that be well explained. It's not binaries that it should plot. But if in their work with some stars and, they form mining, you could also have, it's really very different on wild also.
Yeah.
Because you have a phase that happens. And so for instance, we have certain phase difference balances and stuff like that, which could be seen as backwards churn with a signal something you don't see. So, the thing that I think it's a great point, but we've been emphasizing that point as well. But it's probably good to bear in mind that the existence of photonic objects do not allow very distinct phenomenologies. Then we will have that niche, then if we don't see them when we have enough statistics, then
Yeah.
it's kind of a caveat, say.
Yeah, no, I agree, and that was something in Mara's paper as well, was there were some, especially for fluffy mini boson stars and, sulfonic models with larger sigma, you would get smoking effects, in the chirp, as you say. You could even get like, she even had some runs where she ran two boson stars that were out of phase and they wouldn't ever even in spiral, they were just floating orbits. And this is just, a long in spiral signal that looks like this. And obviously, if you see something like this, then that's very strong evidence that there's something weird out there in the universe that's not a black hole binary. But yeah, I mean, with this, I think there's kind of two perspectives, if you like, from which to look at boson stars. One of which is sort of from that side, which is, could they be out there as dark matter candidate objects in whatever form? And the second one, which is more, I'd say, sort of when we take this project, which is, let's just use them as the simplest possible model for any kind of ultra compact objects, non-ultra compact objects. And they're very good numerical stand-ins because they're easy to evolve and so on. Maybe we can say things about more generic objects, about whose particular matter properties we're agnostic. So we won't infer too much about things that are kind of clearly specific to the scalar dynamics, or it's like this.
More release. Maybe I haven't or practical details. So you run this simulation for quite a long time, it seems. How many seconds a day can you have real world side?
So I think our longest ones are getting up to 3 months now. Yeah. Now obviously, this is just kind of like I mean, for some things, like for a in spiral or such, you have a particular time that you want to run for, and that's it. Obviously, for this kind of project, you run it for as long as you can, and the longer you run it, the more compelling your evidence gets, I suppose. We've just been running, you know, uh, like even now the paper's in review, we continue to run it because, in case they say, oh, we want you to run for another 10,000 time units, and we say, okay, we run for times that 10,000 time units. But yeah, very long in real world times, really.
Any other question?
Some people would be taking on, say, in the same time scalable, would be fairly easy for you if you had initial link.
Oh yeah, absolutely. Yeah, I think we finally responded to your email about that. Once it's released, once it's full. No, that's okay. We weren't. Yeah, no, we weren't fast either. So don't feel obligated. But yeah, Uli was very busy.
But that's people.
Yeah, no, absolutely. Yeah, we definitely have to do it.
Maybe some questions on Zoom? in the meantime, there were any objects here. Doesn't look like, so I think we can see the 10 gallons here.